Sounds great.
We're on.
Yeah, that's LAAS.
We're on? Wow. Welcome to All Space Considered, everybody. That's our smoothest start yet.
It actually is.
It's a great way to start tonight's show because we have a heck of a show for you. All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks in the city of Los Angeles. And as always, we like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. Now, All Space Considered happens the third Thursday of every month, except when it doesn't. Every once in a while, we change the date if we have to, but so far we're doing pretty good this year. So this is our first show this year, and it's the third Thursday. And next month is going to be on the third Thursday, so keep that on your calendars. We've been pretty good about it. It is February 20th, 2025. And we have the Astronomy News Bulletin for you, so we're going to cover some news. We have a story about Parker Solar Probe's closest approach, some lava in Hawaii. Yeah, don't look up. Something might be coming. And some interesting news from Bennu, the exciting molecules that are there. Then Jared's going to do an out to launch for us, which will be a lot of fun. And then we're going to rank the 245th AAS stories. Now you might be like, what is that? Well, that is the big meeting that happens every year, the big ones in the winter, where the American astronomers and people that belong to the society all get together and talk about the biggest results they have. It's actually a big meeting for students and postdocs to try and get jobs. It's a big job fair, but a lot of great science comes out of it. So we have about 400 results to cover with you. Okay, not that many, but we've got a lot. So if you hate a story, keep in mind a minute or two later, it'll be something else. Although there's a lot of black hole results. It's a little crazy. Anyway, this first, oh, by the way, I want to introduce the panel tonight. Laura May Brown is with us, Bill Gruneberg, and of course I mentioned Jared Head already. So thank you all for being with us tonight. And thanks to everybody that's watching on YouTube and here at Griffith Observatory. So first of all, I do want to talk about this image that's in the background here. This was a new image taken by the Euclid telescope, and it is of a big elliptical galaxy, as you can see. It's a little bit disturbed. You can see it's not symmetrical very well. There are these weird little loops coming off of it. And when you zoom in, you see something interesting. You see this weird ring around the very, very center. In fact, zooming in even more, it's an Einstein cross. That is caused by gravitational lensing. The gravity at the center of that galaxy is so strong, it can bend the light coming from a background galaxy. And indeed, that arc you're seeing there around it, those four bright spots, that's why they call it a cross. It sort of makes a cross there. But that entire ring and that arc is a galaxy that's behind the one in the foreground. And the light's being bent around, making this ring. And it has to be a perfect alignment of the galaxies to make this happen. So it's a really pretty image. And you can find this if you Google Einstein ring and Euclid, if you want to read more about it. So Laura May, the Parker Solar Probe did something really interesting.
It was right after Christmas. Parker Solar Probe is a mission that, as its name indicates, is looking at the sun. And in fact, not only is it looking at the sun, it's the closest probe, the closest thing we've ever sent to the sun. And so it set a new milestone. I think it was a couple days after Christmas, if not in the new year. But also just to let you know, so its instruments are protected by a 4.5-inch thick carbon composite shield, which can withstand temperatures reaching nearly 2,500 degrees Fahrenheit, or about 1,377 Celsius. So it is really quite a tremendous feat of engineering. And its primary goals are to examine the acceleration of solar wind through the movement of heat and energy in the solar corona. So if you've ever seen a solar eclipse, maybe you saw the solar eclipse last year or the one in 2017. This is an image I shot in 2017. You might have seen it's the only moment when, as humans, we can actually see those kind of enormous tentacles that stretch out from the sun. And we don't understand kind of how it works or why it's hotter, in fact, than the surface of the sun. So there's a lot of mysteries about the sun, and so the Solar Parker Probe is trying to understand some of the functioning of all of this. And at the closest approach, it will be going around the sun at about 430,000 miles per hour. That's pretty remarkable, right? So that's fast enough to give you a little comparison. That's fast enough to go from Philadelphia to Washington, D.C. in 1 second.
Yeah, that's the fastest any spacecraft has ever gone.
Yeah, so pretty remarkable. Whether this video will load or not, perhaps not. Okay, apologies, we had a video that showed the coronal streamers on the sun. So these were bright structures of solar material. But I don't know if we actually have...
play.
Did it play?
No, it's not.
It's always dicey for us to have videos sometimes in this. But it has made quite a few discoveries. So those are basically bright structures of solar material in the sun's corona. And this is to show you the orbits. So this is the launch that you can see on here on the left side. So on July 31st, 2018 was when we launched it. And so it's done a series of, in fact, Jared, you're probably familiar with these kind of trajectories.
Yes, these gravitational systems. I was going to say, it's not a very big probe, it's only a couple 100 kilograms.
Yep.
And in addition to that, they launched it on a Delta IV Heavy, which is something that can lift or used to be able to lift somewhere on the order of 60,000 pounds to low Earth orbit, like a tremendous amount of weight. And then in addition to that, they put a third stage on top of it as well to give it some extra oomph as well, basically to slow it down to dive in towards the sun.
If people think the sun will pull things in, but you're going at the orbital speed of Earth, you've got to get rid of all that speed Earth has in order to fall inwards, and that's hard to do.
So they basically use this big rocket with an extra stage to slam on the brakes as opposed to speed you up to head you out. So.
Pretty amazing. And so it had on December 19th, basically the closest approach we've ever had to the sun at 9.86 solar radii. I don't know how you pronounce this in English.
Radii.
There you go, radii. So extremely, extremely close to the sun. So to give you these numbers, so its fastest speed, 426,709 miles per hour on December 24th, and closest approach, 3,832,320 miles. So that is extraordinarily close to the sun. I'm honestly shocked that they've managed to, and it survived. So I think the data download is still on its way. They're still waiting for the data, but they know it survived.
They got some data from it, but not all of it yet, certainly. So.
Yeah, right now it's closer to Venus right now, so it's looped back around. So we'll have to wait and see what kind of results.
It called home, said, "I made it. I'm safe. Here's some basic stuff." But they're waiting. Yeah,
it was pretty amazing. Next, a different volcano than we have spoken about on here. You might be wondering what they look like in the distance, this kind of reddish glow that we can get. So this is an image I shot a week ago on the way to Volcano National Park. This is in Hawaii, where they have very, very frequent eruptions. You might have heard about some of the volcanoes there. Some of them have been quite devastating to some of the communities there. But some of them are also nice, what we call tourist eruptions, right? And so let's have a look. So this is a map of the Big Island part of Hawaii, where we have some of the most active volcanoes on Earth. So this is showing you the lava flows and what has erupted since the 1800s. And the volcano...
And by the way, I want to point out we have some of the world's largest telescopes on top of Mauna Kea over there as well. So it's supposed to not have any more lava flows.
Yep. In fact, Mauna Loa also, which is the largest volcano on Earth, and it had a solar observatory up there, which is currently not accessible. They said they would reopen it last year, and it's still kind of on hold. But yes, Mauna Kea, that's where we get a lot of our biggest telescopes. And so Kilauea, right down on the bottom, that is where this eruption was. So this is an image I shot just about a week, 10 days ago, of the eruption. And it is, again, one of the most active volcanoes on the Earth. And it's been erupting for approximately 210,000, 280,000 years, right? So pretty amazing. It was erupting underwater, and then it slowly transitioned and became over the water. And those are cyclic eruptions that date back. So we right now are in a series of cyclic eruptions. And when you look back to the 1800s, there are eruptions that last 35 years, and there are eruptions that last just a couple of hours. So with occasional pauses in those 35 years of a couple days or a couple months. And an older one that was witnessed by people and recorded lasted about 60 years. This eruption, however, lasted fewer than 20 hours, believe it or not. So this was in the middle of the night. I went there, in fact, with one of our audience members here, Bryce, and we got to see it in the middle of the night. Really, really magnificent to see that eruption happening. It had some fountaining up to about 300 feet up in the air. And to show you, so that's what it looks like from right behind the crater. So right behind, so that is a fountain, again, that is reaching about 300 feet.
I hope you're not really that close to it.
You know, we're pretty close.
Really?
Pretty close, but I know, right? But long lenses
Yeah,
as well, right?
sure.
Long lenses. And so right now it is in a cycle of non-explosive eruptions, but it is expected to at some point return to explosive eruptions. Hopefully not anytime soon. We hope so. But it will return to that. And this is a project that I did last time. The eruptions that I've gone to in Iceland, where I've been documenting them through painting and also sampling active lava flows. I was taught how to do this. Do not do this at home if you have a volcano. But I was taught how to sample these lava flows, so I did so on a canvas. And so again, once more, this was at 6 o'clock in the morning, or I started around 5 o'clock in the morning, and did not sample. It's important to keep in mind that Hawaii has a different cultural approach to their volcanoes in comparison to Iceland. So it's important to respect cultural traditions there. And I've added quite a few, so I usually add quite a lot of science to it. So there are some important equations that relate to the magma ascent velocity equation, the volcanic plume height equation, so on and so forth. And this volcano, as I was telling you, lasted fewer than 20 hours. So in the back, in fact, that was right when I finished, and it waited for me to finish my painting. It's a very polite volcano, very considerate. And it started erupting again yesterday and just finished about 2 hours ago. We were going to load the live webcast, but it lasted 13 hours, and then it was done. And so that is what it looked like. And I felt terrible for people who arrived right at that point and said, "Where's the lava?
Where'd it go?
And
I just
we're
got
like,
here. We stopped for the nene."
And so listen, if you ever hear of an eruption near you, you must go right away. Volcanoes, things like that, you really have to go check out lava.
Yep.
Right away.
So in the news, there's been talk about an asteroid coming. Has anybody seen that in our audience? You've seen that? Yeah. Well, this is what Laura May found for us.
There's some great ones, really.
It's approaching, and it's approaching fast. Of course, our team thought of this movie. Now, this is not a planet killer. This is not something that's going to come in and destroy us. I want to say that right now. We don't want people worried. But Laura May, you've actually done some science on this at this point. In fact, it was while you were in Hawaii.
In fact, so this coincided with the eruption. So as you know, it was on the news recently. It was discovered, in fact, just about a month ago. And so here is the predicted orbit of the asteroid 2024 YR4. We'll call it YR4. So it is what we call a near-Earth orbiter, right? So we track and we know a huge amount of these, right? The majority of the very large ones we know, and they have orbits that cross our own, which is why we're very careful. And a lot of people work on these, and they try to identify what their composition is, all sorts of things like that. So here you can see it goes almost as far as Jupiter. So that outer line, that outer yellow line is Jupiter. And then you can see us. And so there was, when it was discovered, a potential small chance of impact. So these are the positions of planets, by the way, shown on January 28th, 2025. And I'll show you this beautiful little GIF, little video of it. It's so small. It was helpful that they circled it. Yeah, so it was discovered on the 27th of December by the ATLAS team, by the University of Hawaii. They also have a telescope in Chile. They have one in Hawaii, of course. And the worldwide network of observatories of the International Asteroid Warning System. And so they've continued to do follow-ups. Lots of people have done follow-ups. But in case you were worried, we did want to show you that it is not a huge concern, right? So this is an image of the Tunguska event. So this is the largest impact on Earth in our recorded history. And so on June 30th, 1908, we had an asteroid plunge into Earth's atmosphere, and it exploded in the skies over Siberia. So these are images, these are fallen trees,
Yeah,
right?
fallen trees. They were knocked down in a radial pattern away from where it exploded in the air. They didn't find any remnants of the object, so we're not really sure what it was. It may have been a comet that vaporized and exploded in the air, or maybe chondrite material they just didn't collect, although you'd think people would find it now.
Can an airburst even do this?
An airburst can do this, yeah. The shockwave can knock them down. There's also reports of a man being knocked out of his chair. He was on his porch. Who knows if that's apocryphal or not, but nobody died from this. But if it happened over a city, would it be a good day?
No, that would not be a good day.
Not be a good day.
So this is to show you the size comparison. So this is the estimated size you'll see of the Tunguska, so about 50 to 80 meters. And this is in comparison 2024 YR4. So roughly not too far from it in terms of size. These are still things that are a little hard to constrain. It was just discovered. It's moving away from Earth. And this, as you might have heard in the news, the Torino scale. It's a 3 on the Torino scale. So this is a tool for categorizing potential Earth impact events by asteroids or comets. And so objects with a scale of 1 are discovered several times per year, so nothing to really worry about. But YR4 did reach a 3, and it is one of only 3 objects to go that high, we had a 3 and a 4. The highest is Apophis, which a lot of people have often heard about, and it was only a 4 for 4 days in 2004. Now, XKCD, some of you may know, the very famous science engineering cartoon or webcomic. I think this is almost a better scale than the asteroid, than the Torino scale. So I guess here where would we be? We'd be somewhere between 10 meters and 100 meters. So yeah, bad news if you live near the city it's aimed at. Probably not great, but not an extinction-causing event. There were modelizations of the path. So this is a map of the impact risk corridor. So this is potentially, if it hit us, where it would land, right? And again, we don't know, depending on its composition, for example, it could be an airburst. This means it doesn't actually even land on anything. There were some talks about it potentially landing on the moon. These are all things that need to be further constrained.
Now, what year would it come by and hit us?
Yeah, so that's 2032.
Yeah, and it comes by once before then, in 2028.
Does it? I'm trying to,
2028. So we'll have a chance to get some more observations of it, refine the orbit even better, and actually maybe figure out what it's made out of, maybe. We'll have to see.
And then the James Webb Space Telescope is going to be looking at it in early March, and then they've also got a month of observation from late April to late May as well.
So these dots here are different simulations, I assume, right?
So this is the region of uncertainty. So again, you can see it's quite wide. It's hard to kind of really see because the Earth obviously is not a flat circle. It's a sphere, it's a volume. But this is just to show you that there's quite a large region of uncertainty. And so this is wonderful data that I reduced, that Bryce, who's here, Bryce Bolin, was able to get from the Gemini telescope. So it might be hard to see sometimes. So those little things you see, the little white streaks, those are cosmic rays on the detector. But right in the center, that little pale gray dot. So that's from February 7th. Its magnitude at the time was about 23.4. This is another image where you can actually see it moving also, just in case it's a little easier, different views. And this is potentially the last image that will be taken of it. We actually got this when we were in Hawaii on the Keck telescope, so pretty much the world's largest telescope. This is an image from February 11th. It was very hard to do because part of the instrument slit was closed and it was partly broken, but that little pale gray dot you're seeing right over the black, that is actually the asteroid. It was very, very, very faint. And just today, this was a great day for us to film this because the impact threat was reduced to 0.28%. So it has 99.72 chances of missing Earth.
Yeah, yesterday they raised it to 3.1%. And that's what we expected to happen, is the error bars shrink. As long as Earth is still within those error bars, the percentage goes up and up and up. But then they shrink and Earth is no longer included and you get these point whatever. So that's great news.
Yep.
All right.
Yeah.
Then why are we even talking about this? Anyway, it's an awesome, awesome piece of work, to be honest. Many of these things we don't see till after they've passed us. But luckily, we have found over 99% of the really big ones that could cause a lot of trouble. So we've 99.9% of the really, really big ones. Ones like this are out there and can still be found. So it's important we look for them. It's important we have processes like this where the information is shared and astronomers can gather the information needed to protect us. Because we do have that thing called the DART mission where we could send a thing up and you can impact it and just push it. And the key is you want to see it early. And if you impact it, you just literally run a spacecraft into it. That adds a little bit of momentum, and that pushes it off the track. And that's the best way to handle these, we found. DART was amazingly successful.
Yep.
No explosives needed, nothing crazy, and it worked really great. So fantastic day for Earth protection. There was another bit of news. I'll try and go through this fairly quickly. There was a mission called OSIRIS-REx that went to an asteroid called Bennu, and it gathered some material. And as you can see here, it comes down, smashes into the surface of the asteroid. They planned a long time for this, of course. And at the same time, it gathered material in that little nozzle at the front end of it, sealed it up, came back to Earth. So it landed on Earth, and sure enough, a bunch of asteroid materials in there. Some of the cool results from that, they saw salt crystals, literally crystallized salt. So Bennu, believe it or not, is made up of sort of rubble from a bigger object that was destroyed. That object had water. The water worked and interacted with the minerals that were present and salts that were there. Evidently, it evaporated and left behind salt crystals, or like the crystals crystallized. These would have been destroyed probably if it had fallen through the atmosphere as a meteor and eventually a meteorite when it landed on the ground. So going to the asteroid and grabbing the sample, sealing it up, keeping it away from water, where these salt crystals would just melt, was super important. In addition, well, there's some more sample information. They found a lot of ammonia, which is a little strange. Ammonia is primarily found very far from the sun. So this says that other object maybe was a little further from the sun than we think it was when it was originally destroyed, or at least when the ammonia got locked up in there. They found a bunch of amino acids. Anyway, these are amino acids that are used in life. It found, I think, 13 of the, however many they're the ones that are yellow were found in the sample. The gray ones were not. But still, that's amazing how many of the bio-creating molecules for life are there.
As asparagus.
Pretty complex looking stuff. At the
Yeah,
bottom
complex
there,
looking stuff too, and this is all the water interacting with those minerals. Now also, all the nucleotide bases that are in DNA were found. Every single one.
Pretty
So
amazing.
everything to make DNA was found on this asteroid. There we go. So anyway, and the way they think they worked is the original body came together, the water interacted with it, created all these complex molecules. That thing got destroyed. Bennu regathered it up, and some of it got processed on the surface. But the fact that it's there, and Earth was created from material like this, and we have life here. But then again, so was Mars. So was Europa. So, we have a lot of places in our solar system that probably have all of these molecules that life needs. So very exciting. There's another mission coming up called OSIRIS-APEX, and they are going to go to Apophis and gather material off of Apophis and bring it back. And that's that asteroid that's a near-Earth one. Its chance of hitting us has been lowered to pretty much zero. But nonetheless, it's another near-Earth asteroid. And learning about these things, are they rubble piles? Are they more solid? How would we deflect them? All of that's super important. And also just the origins of our solar system are locked up in these objects. It's really, really cool. So fun missions. Yeah. So Jared,
I was going
to say, some out to launch.
With OSIRIS-APEX, one of the things I'm looking forward to is that it should be arriving right as Apophis is doing its very close pass to the Earth in 2029.
Oh, nice.
So hopefully we can get a really neat image from it of Apophis with the Earth in the background.
Oh, wow.
So I would love to see that
Very
with,
nice.
an asteroid and a planetary body.
An Earth selfie. So.
Yeah, essentially. We could all
Pretty
wait
awesome.
at that time.
Yeah.
So just a little bit of news about what's been going on in rocketry. Since we were last here in December, the Starship 7th flight test flew earlier in January, and there was great success for the first half of it, and we'll talk a little bit more about what occurred during the second half of that flight. But this is flying out of Boca Chica in Texas. You can actually go and watch these if you want to, if you feel like making the road trip out there to catch them. This rocket is massive. Starship Super Heavy is about 400 feet tall, and there's a view from Starship of the Super Heavy booster separating and then burning its engine to return. And this being the 7th flight.
400 feet, how many stories is that?
Many stories. So
yeah, it's like
30 stories. Something
Yeah, I think
like
it's
that.
taller than City Hall.
Yeah, the Starship is actually bigger
silver
than
flare
the space
coming
shuttle.
back to the once again we are standing by for attempting to catch the booster at the tower. This would be the second tower catch.
Landing bird. Seeing 13 engines.
Are we expecting another chopstick catch?
Yes,
They're now
this
hovering
was
as it
their
aligns
second
with the
successful
tower for
chopstick
catch.
catch.
Or was it?
Down to 3 engines.
Yeah, that's pretty wild that they're capable of being able to do that. That's all a part of the rapid reuse, basically move the chopsticks down, get a Starship on top of it, refuel everything, launch within a couple hours.
Do
That's
they
the
have
plan.
to inspect the whole thing before they use it again? Or?
So at the moment, yes. What they're planning to do is to have very simple inspections, almost like what you would inspect with an airplane between flights at that point, whenever they reach that. And I enjoyed this, seeing it kind of easing back and forth on the chopsticks there. But if you're very attentive, like I enjoy being during the launches, someone who's an aerospace engineer who works on rockets, something was starting to happen here. This is a diagram showing the engines on the Starship spacecraft. We've lost one of the center Raptor engines right there, and then we are going to lose another Raptor engine here in just a second, and we're starting to see that the speed is not moving, it's not accelerating as hard as it was. Okay, we've lost another center. Okay, now we've lost one of the outside vacuum engines on there, and now it can possibly make it to orbit at this point, but it's going to be a little bit difficult to control the vehicle in order to do so. And okay, maybe we're not going to make it to orbit now at this point. And then we're going to lose control of the vehicle entirely at this point. And then telemetry stops from the Starship vehicle.
Yeah, that's usually a bad sign.
Yeah.
Yes. In the rocket business, we call that not good.
Yeah.
So, and if you're wondering, well, what happened to it? It looks like there was a leak of propellants that were coming out of it. It started a fire and basically shut down the engines and caused it to go a little bit off course, which meant that if you were in the Caribbean and you got to take a look up in the sky, here comes Starship, everybody. So the flight termination system activated, it destroyed the vehicle, and this is the little bits, or I should actually say sizable bits of Starship re-entering the Earth's atmosphere.
Wow. I
after
love
that
the
flight.
commentary by all the folks in, like, bars on the beach, drinking their drinks and being like, what is that?
Yeah. What is that? Whoa, this is so unreal.
Yeah, there were
I
a
can't
lot of
believe it.
posts on Reddit and things like that. People going, "Oh, look, it's meteor shower."
Yeah. No, well, of a metallic type.
Nobody said aliens, right? I hope.
Probably some people thought it.
But I just thought this was amazing, being able to see this.
Wild.
And if you ever do film something like this, it actually is helpful to get this kind of footage back, because it does tell us things about what those parts were doing. Like, there were several of them that I could see in this that were tumbling, and that can actually tell us things that were occurring post-flight termination system, which is very, very important. And my personal favorite video is this one here that a gentleman took on his flight.
Oh, wow.
Coming in. So imagine being on your airplane and looking out the window and you see this.
Yeah.
So this looks like it's right by the airplane, but one thing you do have to remember is that this is several hundred miles away. So it looks low to the horizon, but it is still about 90 miles above the surface of the Earth, and basically about 15 times what you're going to be in your airplane. So it did burn up. It did end up causing flight disruptions. So there were quite a double-digit number of aircraft that had to be turned around from the area that Starship re-entered in. And this was expected if it did have a problem, but it was a bit unexpected in that nobody was really thinking that it would actually happen. But hey, surprises happen all the time when you're testing, right? Yeah.
Well, when your testing philosophy is push hard, break stuff, and then fix it after you break it.
Yeah.
And you can do that when you're doing test vehicles like this, but
Without people.
not without people.
Without
exactly.
people,
That's my
yes.
key. Or without really expensive space probes or things like that. So
Yeah.
this is all the testing phase. So
Yeah, this is
fine.
all on their dime at this point, so they're
Well,
kind of
some of this is government dime. SpaceX has been funded by government contracts,
to
and still is.
to a degree, yeah. But ultimately, you don't want aircraft flying in this area. They kept the area closed for about an hour, and a lot of people were like, well, why do you want to do it for an hour? And it's like, well, all those little bits are still coming down. You know, even things, the size of your fingernail, hitting that at 500 to 600 miles an hour in an airplane, not a good idea.
Going into the end.
Not particularly great. But they are getting ready to do Flight 8 next week, so they have gone through their own FAA investigation, which, if you're wondering what that is, basically, SpaceX runs the investigation, and then the FAA clears their findings on that there, and they have, and the what are called notice to airmen, or basically the keep out areas for aircraft, have been published for both the United States and Mexico. So when we see Mexico publish theirs, that tells us that it is indeed on. It's going to be happening next Thursday, sometime in the afternoon. So we'll have to see if this one goes a little bit farther than the Caribbean. I mean, honestly, if I were on a flight, I'd stop off in the Caribbean too. But you know, I'd rather make my target.
Is the disintegration process manually triggered, or is it an automated process?
So very interestingly, the flight termination system on these vehicles is automated. So that actually allows a simplification of the system involved in it. So essentially the computer figured out, I'm starting to go in places I'm not supposed to. I'm going to go ahead and fire the explosives. And these explosives, they're not designed to basically make the vehicle go kaboom. They're basically designed to make the fuel tanks rupture wide open. And then from that, your vehicle disintegrates. Because you actually don't want it to go boom. That can make even more debris. You want the debris to be of a size that allows it to re-enter, just like we saw. So it went according to plan with that. So another thing I do want to tell you a little bit about is that we do have some lunar landers coming up as well. Firefly Aerospace's Blue Ghost mission is actually going to be landing on March 2nd. So they're in orbit around the moon right now. Very excited for that. And then iSpace from Japan, their Hakuto R Mission 2 is going to be landing sometime in April. So I'm very excited that we are getting into this age of every couple of months we're going to start landing something on the moon. So
very fun.
Yeah, looking forward to it.
Very fun. Well, now it is time for us to transition to the second half of our show. More or less perfectly on time, too, which is amazing. But I'm going to introduce this board over here that you're seeing, this felt-covered piece of plywood with some strange letters on it and some colored astronomers' monuments from our front lawn. Well, what we are doing is we are going to do a tier list of the top stories, the top research discoveries that were announced in the AAS meeting, the American Astronomical Society meeting that happened back in January. And we thought what would be more fun to try and rank a couple of dozen stories than to do a tier list. Well, originally we thought, well, let's do maybe like energetic things in the universe. For example, like, gamma ray bursts or solar flares, or Taylor Swift is,
that was the
she's the superstar tier. So,
clear.
And then we thought, that's a little confusing. Let's go with something that's a little more astronomical. And we landed on doing stellar classifications. And O-type stars are the biggest and brightest ones out there. They have temperatures of 60,000 Fahrenheit, and they're, 10,000 times brighter than our sun, or 20,000 times brighter. B, a little cooler, a little fainter. A, again, cooler. F, G, K, M. And you might think these are some crazy letters, but okay, we'll roll with this. So we put them vertically and we mounted them on the board and we colored them the color of their stars. Now there is a little bit of a story where this comes from. These are actually spectral classifications. Upstairs we have a spectrograph and it shows the sun's spectrum. And indeed all these little black lines are in there. Those are caused by the atmosphere of the sun and the elements that are there. The hot glowing sun, the light passes through it, and some of the colors get absorbed by the elements that are there. These big dark bands you're seeing going vertical, those are caused by hydrogen, the most obvious ones. And initially this sequence, of course, they were ranked A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. It was very complicated, and they weren't in a scientific order necessarily. Well, this woman, Annie Jump Cannon, was doing research. In fact, she was an exceptionally good stellar classifier. She could see these spectra and classify dozens of them per hour, which is kind of crazy to be able to go in and get accurate classifications of stars. She did thousands and thousands of stars. In fact, she was part of the Henry Draper catalog, and she went to her colleagues and said, you know, this order is not correct. It should be O, B, A, F, G, K, M. She was basing it off the strength of the Balmer lines, more or less, but also rearranged it a little bit. Later, it was confirmed that indeed the order she had picked was a sequence of temperatures, and she got it right. So there's an award that's given out that's named after her at the AAS meeting every year, well, most every year, and it's called the Annie Jump Cannon Award, named after her. And it's pretty amazing. The first person to get it was in 1934, the year before Griffith Observatory opened. It was in December of 34, and it was Cecilia Payne Gaposchkin. I have a hard time saying her name. She had a hypothesis that the sun and other stars actually had other elements that were different than the ones that were found in like planet Earth or the moon. She said planets and stars have different compositions. Well, it turns out she was right. Indeed, the stars are primarily hydrogen and helium, and they have a smattering of smaller elements. In the planets, of course, we've got lots of silicon and iron and things like that. So, amazing thing, and she won it literally just months before the observatory opened. So tonight, to celebrate Griffith Observatory's 90th year, which will be officially in May, we'll have our celebration, so check our calendar, we'll have events and all sorts of fun stuff, but every month on All Space Considered, we want to bring a little highlight of how Griffith Observatory in the past 90 years has been connected to things and a little of our history. Well, we have a connection to the American Astronomical Society. In fact, if you go back and do a search, I know it's such an exciting slide, visually pleasing, but if you go back and search, you can see that indeed folks that work here have been presenting papers at this meeting. And you can look back in, I guess, what was that, 94? Dr. Krupp had one, and then another one that I didn't circle. I don't know why I forgot that one. He had another one delivering a starry message. Above that, chemical composition of bulge stars. Oh, that's me. I'm on that paper. I'm the one more in there, and one more.
We have Anthony Cook.
Yep, Anthony Cook's in there. I'm on another paper, the Brava survey, is me. Dr. Krupp again. I'm also in the 11 more, I think. No, that's Dr. Krupp is in the 11 more, but anyway, so the few of us are in there, but also Laura May, you've done research, but you just haven't published at the AAS yet.
One day.
One day. So we'll get you there. We'll get you there. But there are folks that have been doing research on the stage, but I love that Griffith Observatory has been involved. In fact, Griffith Observatory Director, Dr. Krupp, won the 2013 Andrew Gamont Award that's given by the AIP, but it's awarded at the AAS meeting. And in fact, here he is giving his talk, and he called it Star Trek, the Search for the First Alleged Crab Supernova Rock Art. And it was an interesting talk where he showed pictures of the moon and other explosions. The Crab Supernova, it would have been a bright new star in the sky that was seen back in the day. The Chinese saw it, but there's very little record of it in Europe. In fact, none as far as we can tell. But there's rock art that has some of it.
Yeah, I think it was in 1054.
1054, yeah. That is correct. I couldn't think of it.
Yeah.
And then here he is getting the award back then. So Griffith Observatory has a connection to the AAS, and in our 90 years, we've had folks present at these meetings and do research. I did a little research to try and see if the other directors had done any presentations at it, and I couldn't find any record of it. They did publish a little bit here and there, but not at the AAS. So it is wonderful to see Dr. Krupp win this award and really represent at the AAS meeting. So it's a lot of fun. But that leads us to tonight, our own awards that we're doing. And in fact, we are reviving the Golden Griffies. Was anybody here when we awarded those last time? A few of you maybe?
Better than the Oscars.
Better than the Oscars,
Yes.
better than the Grammys, the Emmys, and more confusing perhaps. So what we're going to do is we're going to go through each of these press releases. There are literally thousands of papers that are presented at this meeting, but there are only a few dozen press releases. We've picked our favorites. I'm sorry if yours got dropped. Anybody out there that's watching that might see yours. But we picked our favorites. We picked the ones we could easily go through and explain to you the best we could. And then we're going to slap them up there on the board. So, now do we remember who's...
And then we will involve the audience in deciding which story gets the gold the silver, and the bronze.
And the bronze. So yeah, it's a little ad hoc, but we'll just have a raise of hands. We'll see how it goes. Now the question is, do we remember who's doing which story? Bill, I think you had a preference for the stellar pyrotechnics at one point.
I did. As I recall, this was a JWST mission. It used the JWST in its mid-infrared range, which is of light. Which travels much, through dense material much better. So the bottom line is, they were trying to look inside this giant star cluster, because the stars on the outside, of course, block your view of the stars on the inside. But if you're looking in mid-infrared range, you see it much better.
Yeah, you can pierce through all that dust that's in the way. In fact, here is the mid-infrared image. You can see that dust kind of disappears from it. So they're able to measure the stars that are down inside and see what they're made of, which is a lot of fun. But that picture with that dust in there, the warm, glowing dust, is a lot of fun.
Yeah, there were some results that are going to lead them to further study because they're very interesting. A couple of really gigantic stars that were doing completely different things, different morphology, they call it.
They were going at different speeds as well. I think they were trying to understand why some were going at different speeds.
Sure,
yeah. Pretty amazing.
So what did we rank this one?
So who's going to be putting them up on the board?
I can put them.
All right.
Sure.
I'm closest. I'll sacrifice myself.
So we did rank these. We had some heated conversations to rank these.
So what's it listed on the back there?
This was an M.
Oh, this is an M. Okay.
Sorry.
I was going to say, there's several letters actually.
Is that
on
French
the back
M?
of this.
No, it's because it was a W. It looked like a W, and then I remade it as an M. And
okay.
There you go.
Listen, guys, there was a lot of.
That's a mighty
ranking.
good story there. Yeah, that's me.
That is a nice story, but it deserves to be a little higher.
You think so?
But oh well.
Oh, well. Okay, so the dining habits of So Well, Bill, we're starting out at the very bottom.
All right,
You got to start somewhere, right?
You gotta start somewhere.
The dining habits of supermassive black holes. Well, this was a okay story. The New Star Survey. New Star's a space telescope. It's out there. It measures things in X-rays. And we expect, based upon how black holes, when they feed active galactic nuclei, when a black hole in the center of a galaxy, these things weigh millions of solar masses, so much mass that light can't escape from the very center. But as material falls in, it starts to glow before it falls through that event horizon. It can glow very, very brightly. It can give off X-rays, and this telescope can pick those up. Well, as the material falls in, we'd expect there to be a big sort of torus around it, a disk of material, and we'd think it would block that light out. And you can see here in this little animation that hopefully plays, that if you have the wrong view, you can't see down to the center of it. But if you have the right view, you can. So just based upon statistics, you'd expect about half of them to be blocked, and about half of them you should be able to look down into the center. So ones that are feeding on material, we think we should see about half. Well, up till now, we've only found about 15% of them are shrouded. Weirdly, why only 15%? How come we're seeing down inside so many of them? Well, this new study found that 35% of them were shrouded, plus or minus 9%. So that's pushing it up closer to 50%, but it's still a little strange. I'll describe what's going on here. The infrared, the red image in the upper left, that infrared light, it can kind of penetrate the torus, and it glows. The visible light in the upper right corner, it can only come out if it's going up or down. You can't see through that disk. The X-rays in the lower right, they can penetrate and get out. They can pass through the torus, but they scatter strangely. And then, of course, blue light is mostly absorbed. The purple light, it can only get out if it's up above. So very interesting story that this telescope found that. And I liked this one. I think, did we rate it a...
we gave it a G.
A G. Yeah, it was great. It was pretty great.
I think it should go up one more. So... because I feel like I understand these black holes, because I'll often be obscured by food myself.
Okay,
and
well,
people will be like, I don't know if he's there.
All right, audience, should we let Jared have his way?
Yeah.
Yeah.
Okay, all right.
All right, so it's an F.
All right, it's an
All right,
F
we're going to
then.
go up.
Oh, what have we
Mom will
done?
love that.
All this planning, and it comes to this. All right, another black hole story. Sagittarius A star, clever name. That's the black hole in the center of our Milky Way. And believe it or not, we have Andrea Ghez, Professor Ghez from UCLA, winner of the Nobel Prize, for proving that we have a supermassive black hole in the center of our own galaxy by actually watching the stars go around it. She's going to be here next month, so stay tuned for that. It's going to be amazing. But other folks have been observing Sagittarius A star. There's our Milky Way, and if you zoom in, and then use the James Webb Space Telescope, you can actually see flickering light, that infrared light coming from the center of it, that mid-infrared light. There's the black hole as measured in the sub-millimeter range, the actual picture of it. But this telescope isn't measuring it in that, it's just seeing flickering infrared. Now, that flickering is due to flares. As material falls in, again, glows very, very brightly. It heats up, glows. That's pretty cool. That's the reason they had so much trouble making this image of Sagittarius A star. The flickering is happening all the time, and in fact, they think what they're seeing is material probably orbiting the black hole as it spirals in, so that flickering is happening. Also, they used a sub-millimeter array, which was the telescope used to make that last image, or the type of light, and it also saw flares, although they happened about 10 minutes after the mid-infrared flares. This is what was predicted. This is what fits the model of this actually being caused by what's called synchrotron radiation. And I don't have time to go into that, what that actually is tonight, but it's moving electrons spiraling around a magnetic field. So it's fitting together, and we think we're understanding the flaring processes around these black holes. So kind of a fun one. What did we give it?
We gave it a B.
A B. I think they did a brilliant job
that's
on
a solid.
this.
That's a solid B, I think.
They paired together work from several different telescopes to build this story, so
really
pretty darn
amazing.
cool. Now, another black hole feeding, and when black holes feed, they can actually have jets shoot out of them as well. Now you think out of the black hole. Well, no, from the region close to the black hole. Once you're in the black hole, you're not getting out. Right. But above and below it, you can generate these jets that shoot out, and they think they saw a sign of a new plasma jet. Here's this circled galaxy right here. They looked at it, a clever name of 1ES 1927 plus 654. Everybody remember that. Name your first child that. I'm going to. Anyway, they used a couple of telescopes, XMM Newton and the New Star Telescope, both X-ray telescopes, to observe this, and then also the very large, the very long baseline interferometer, the VLBI, which is a radio telescope. So the radio telescope saw this. Now that's stretching, ignore that. But look at the lobes that are moving away from the center. First they're close, they're a little further apart, and then they moved even further apart. That's the sign that there's a jet that's just been formed, and the jet's moving away from the center of the center of the black hole that's there. So pretty darn...
And moving very fast as well. You can see the dates on there. It's wild. I'm trying to remember what they'd calculated the percentage compared to speed of light.
About 33% the speed of light.
Right.
Yeah, 33%, so a third the speed of light, so crazy fast. 33. This was good enough to get, did we give this an A?
Yeah, we did give this an A.
Yeah, I think this is A work, moving that quickly.
I agree.
To be able to see this.
That one's pretty good. That's awesome.
Now, same galaxy, but with the X-ray telescopes now, like I said, it was observed with several different telescopes. They saw flickering in the X-rays that matched sort of the signs of, well, again, a jet being created and being formed in there. It's consistent with a flaring process. So this was sort of part 2 of it, and I think we gave it an A as well, just because they were paired together. It was more or less the same story with 2 pictures. Yeah. So another telescope.
Jets are really common in black holes, though, aren't they?
Yeah. It could be the oscillating of the corona in there. It could be related to the base of the jet. We're not really sure what's causing the flickering of the X-rays, but maybe something spiraling around the black hole very close to it as well. We're not sure. Triggered by a cosmic dance. Yeah.
I think Jared said he was going to get up and dance to this one.
Yeah.
Just
moves. Get down on it.
So on this one, they observed another quasar, another black hole eating material glowing very, very brightly. This one's kind of strange, however. So at first it was dark, it was not active. And then all of a sudden they measured it and they see a bright activity, a jet appear. Again, we've got these jets appearing out of nowhere. So in 1995, no signs of a jet. 2017, all of a sudden there's a jet there. Here's the galaxy. It's the one in the left center, the very bright star-like object in the center. That's the quasar, the very bright glowing spot of that material falling into the black hole. Well, there's that weird galaxy to the right of it that looks like it has a ring around it. There's a ring galaxy. Could they be related? Maybe. We don't know if they're at the same distance yet, so that part of the story we're not reporting on yet, but maybe. What we think's happening here is that quasar, it's in a host galaxy. It looks like it has spiral arms. The authors reported it as being a spiral galaxy. I don't believe them. I believe that spiral structure is probably tidal debris. in all the interacting galaxies I've seen. And in fact, they even mark tidal companion. And you can even see debris that does loop around and connects to that spiral structure between the two galaxies. So this little companion here. And then if you subtract the two, sort of the model and the residuals, you can see that tidal tail does stick out. So that galaxy's interacted with something. Just like our moon causes tides on the Earth, if a small galaxy passes next to a big one, you can sort of launch these tides that come off of the galaxy. They also observed it with a long-wave radio telescope called LOFAR. And LOFAR showed that it had these lobes around it, these radio lobes. Those are consistent with a jet that happened a long time ago, but the jet shut off. So they're seeing signs of a jet that just is happening now, it's just starting. They see signs that it was shut off, and they see signs that it had a jet in the past. Could this be periodic? Could it be doing a jet, then no jet, then no jet? Well, if that little companion there, if it's orbiting, maybe it's sort of causing them. Maybe it gets close, drives material into the black hole, makes it active, and then you get these flarings. So this is the working model they had. Galaxies interact, radio jet forms, the radio just blow out there, you get the lobes, they shut off, the interaction ends. So it's sort of a cosmic dance, them going around forming these jets every time it comes around. It's a nice story, I really like it. Is it what happened? Maybe. Or maybe this galaxy flew through the center of the other one, which creates that ring, which that's how those get created. When one galaxy flies straight through another one, you set up these rings in them. Who knows? It's a cool story, though. It really is. I like it.
What did we rate it?
We gave it an F.
Yeah,
So,
I
which is
like
good.
it. It's
Which is
fantastic.
Yeah.
Well, all of these are
There's
great.
no bad.
These-
There's
these
no
are
bad.
bad
All
ones.
these stories are incredible.
It's fantastic.
Yeah,
F
every
is almost
single
as
one
good
of
as
these
A
was
in this ranking.
was chosen to be a press release at the American Astronomical Society meeting, and there are thousands of papers, and only dozens are chosen to be big press releases. So again, this isn't anything bad or good like some of these tier lists.
And
Laura
next,
May.
next we have something about the sun. After all of these black holes and galaxies getting a little closer to home. So this is a story or a discovery about the moments before solar flares. You may know that we are in solar maximum right now. So that is the peak of our 11-year solar sunspot cycle. And it's some of these regions, some of these active regions, will produce solar flares. You've probably seen them on the news. They also end up being catastrophized quite a lot. A solar flare will destroy humanity. That kind of thing. But we do want to know, most of them are fairly innocuous, but we do want to know when they happen because they do have a large amount of influence on our technology. So they can affect GPS, they can affect aviation, satellite technology. And so we can look at flares in, we can look at flares in different wavelengths, right? Different types of light, and we can get different information. And so these discoveries and this research was done by a group led by Emily Mason, I believe. And so they looked at 50 flares that were on the edge of the sun. Now that's important so that you can really get a good visual and a good understanding and a good analysis of the light on these little loops that you see. And they looked at at 50 flares, edge of the sun, for about 6 hours before each flares, and they analyzed the light. And they actually found they had some really interesting results. So coronal loops, those little loops you saw, let me go back on the previous image, those are field lines, right? So it's a little similar to that science demonstration you might have seen, perhaps in school, these iron filings and magnets, but they're made of gas, right? But similar kind of thing. And so the loops above the flaring active regions were more variable than the non-flaring cases in 60 to 80% of the time in all wavelengths studied. So that's pretty significant result. And they observed these very small flashes of UV light, right? So again, this is a very, very big step towards understanding solar flares and towards being able to predict them. Right now, it is very, very difficult. We look at magnetograms, so we look at the magnetic fields of all of these active regions to try and understand if some regions are more dangerous than others. But honestly, I think I'm a little biased, and I'm not trying to influence the vote of the audience, but maybe I am. I think this is one of the most important stories to come out of it, honestly, because this really affects us directly. The sun affects us, and yeah, it's a pretty amazing story. Yeah. I think I pushed for an O rating on this one.
Yeah, and I don't disagree with that at all.
Yeah,
That's
well,
a
flares
solid-
are
solid
powerful,
up.
so it's definitely a no.
Yeah,
very
really solid.
energetic.
It's up there. It's S tier.
Perfect.
So now, how did we leave the OBAFGKM on there? If you're wondering what those OFAR folks are, I don't know. They weren't there earlier today.
So
with Gremlins.
So one of the more interesting stories as well that on the surface may not seem like an interesting story is about a region that was discovered by Charles Messier. If you are an amateur astronomer or you've looked through telescopes, you might have seen this region or you might have imaged it, and it is featured in this constellation of Lyra. I don't know how you guys pronounce it. Lyra. And it is called M57. It is the Ring Nebula. It's an absolutely beautiful region. So here it is. It's a planetary nebula. So that means it's a leftover from a star that's turned into a white dwarf. So we have all that envelope that's been shed and that creates this incredible ring, right? So on one side we have the Hubble Space Telescope image, and on the other side we have the view from the James Webb Space Telescope, again proving that they are complementary telescopes. They do different things, they see in different wavelengths. But believe it or not, the structure of the ring has been hotly debated because we are seeing it from our specific vantage point, and we don't fully understand what the exact structure is. It a ring? In fact, it took them a little while originally after they found that nebula to find where the actual white dwarf star at the center was, and it's not perfectly at the center. So someone created, we had it in the deck, again, my mistake on the videos, but someone created a 3D modelization of it. Ooh, is the deck frozen? No, there we go. So someone created a 3D modelization of it and measured even the velocity distribution. So I will point you, perhaps we'll have to link this maybe on our socials so that you can actually see it, but it's pretty incredible. So everything is kind of residing in a clumpy shell. It's basically barrel shaped. It's not cylindrically symmetrical. And they made a 3D modelization of it, which I think is pretty remarkable. And there are even holes in it that are caused by faster outflows, and they think perhaps caused by interactions with a binary, so another star in it. So actually a pretty amazing, I don't know if that's the first time we've ever done a 3D modelization.
No, we've seen some of these like that, but this one was done in better detail, I have to say.
So what do we rate this?
We gave it a K.
Yeah, okay. That's good. That's a good story.
I think that's not bad for it.
So next we had our expanding dusty fingerprints.
Yeah.
We had great fun, by the way, coming up with little titles for each of these. And so the image you're seeing, it relates to expansion of dust shells around a massive binary star system. It's actually a star called WR140. This is a Wolf-Rayet star. These are very, very massive stars that are very, very windy. And so the dust shells are created when the stellar winds, there are two stars, and they collide during these eccentric orbits that they have. So they get a little closer to each other every now and then, and this creates this kind of we have these collisions. And so they were able to, and it's moving, by the way, at about 1% the speed of light, and it's non-uniform. So it's pretty amazing. Let me see. Yep. So this was a tracking of the winds from that. There we go. So this is to show you what configuration these stars are in. So again, we've got occasionally those stars come a little closer to each other. And you can see the difference between the two. So they weren't able to subtract out those diffraction spikes. They were explaining it was a little bit difficult to do, but they overlaid, so there's blue and orange. And when you look a little closer, you can actually see the movement. I believe they were moving at about 1% the speed of light, these dust rings.
Yeah.
Pretty remarkable to see this.
Yeah, it's crazy. The stars, when they orbit, you can almost trace out the path of the orbits in these dust rings because it's the shock wave between the winds from each star. So as they come close, there's even clumps along these stripes. And they get fainter as you move further away, which is an indication that dust is thinning out. It's sort of, but there's so much information in here.
Yeah,
it really is like a fingerprint we could analyze. It's amazing.
So amazing story. This was a close-up view where you could kind of see, again, the different thickness, and then when they overlaid, there was one in orange, one in blue, so that you could really tell the difference. All right, what did we rate this?
We gave this one a B. So way up there.
Way up there.
I think that
really,
works well
really
for it.
amazing result.
So, yeah, very energetic. So perfect.
Good fun. And folks, if you have questions in the audience, feel free to raise your hand. We might ignore you, but keep waving it. Keep waving it if you have a question. We'll try and get to you. So supernova in the teenage universe. Bill, you like things that are really far away in supernovas. What can you tell us about this?
Well, I did not work on this one, I don't believe, but it's I can read it.
We had so many stories, by the way.
Yeah.
We went through dozens and dozens of these and tried to kind of assign these cohesively.
So this is one of the most distant, which means the most long ago, one of the earliest supernovae and it was discovered through JWST again, billions of light years away.
Yeah. It's part of the JADE study, which is a survey where they're looking at lots and lots of supernovae. And transient objects, meaning ones that appear and then disappear, well, that's like a supernova. It explodes, it then becomes bright enough for us to see, and then fades away. And in a single field, I had the field up there, in the single field there were 80 supernovae that were detected, which is pretty neat. And one of them was really, 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 really far away. In fact, there it is, AT 2023 ADSV. So they add the letters to the year that it was discovered. This is the image. It was discovered in 2023. That's where it was brightest. It was a core collapse supernova of a supermassive star and about 6 billion light years from Earth. So we were looking back at a time when the universe was only about 2 billion years old, and this is probably one of the first ever detected supernovae in our universe. So one of the first ones we've seen going off. And the star was a little different than the ones that are closer to us. This took a long time to fade. So kind of strange.
Yeah.
So Bill, what would you rank this?
I'd probably give it let me see, maybe a B.
Yeah.
What do you think, a B?
I think it'd be.
I think it's
I
pretty
think
bright.
I think
it's pretty energetic.
I mean, it is
It's
the
pretty brilliant.
furthest supernova we have ever seen. So
Yeah, that's
very
pretty cool.
It's pretty
I do
great.
like far away stuff, and
It's in the teenage universe. We've all been
It
there.
is.
Yeah, that's right.
Well, now we got little red dots.
Oh, you have a question?
Question over here. Yeah.
What is a supernova?
That's a star that
question.
explodes.
Great question.
A star, when it gets to the end of its life, runs out of fuel in the center, and it has nothing to keep itself hot, so it starts cooling off. Well, if you cool off, gravity can start to squish you, and that's what happens to the star. Gravity wins, and it collapses in the inside, and that causes the star to finally blow up.
blows
So it's
all
an
the
exploding
others.
star. Don't worry, our sun's not going to go supernova. You've
Can't
got
do that.
billions of years and nothing to worry about. So yeah, you don't have to worry about that. These little red dots to talk about here, another story, but these were discovered by JWST in the really, really, really early universe when it was only hundreds of millions of years old, some of these.
it's a baby.
Little babies. And they thought, well, these things, if they're this bright, they must be gigantic galaxies. And people were saying, cosmology is broken. And then people like me were saying, well, wait, we don't know what they are. Maybe they're just really bright and not necessarily made of stars, and they're not that massive. Maybe. Well, that's the case. They're black holes. They're shrouded in dust and gas, but they are accreting matter at an incredible rate. So they're really, really bright. So there's still interesting physics happening. It's still pretty crazy. But these little red dots, they're numerous. They're more numerous than previously known bright quasars, but we kind of know what they are now. We need to study them, but they are the central regions of galaxies as this material is falling into them. So the little red dots are kind of being understood. So I think
What do we rate this?
We give it an A.
yeah, I thought it was an A.
Yeah.
It was
I think
good
it's
work,
pretty
but it
good.
wasn't brilliant. It was awesome.
Yeah.
And they're not that little when you get up close to them, right?
No, they're not. They're black holes.
Like little chocolate donuts.
Yeah. And speaking of, they gave me all the black hole stories. Did the joke ever make it in? I think they were, anyway. So black hole archaeology, again, digging into what's going on near the black hole. Again, a black hole is a region of space that has so much mass that light can't even escape from it. And we think the centers of most galaxies have these. So when JWST was used to go in and look at the centers of these black holes, strange things happen. They notice, you can measure how fast they're rotating by getting a spectrum. And the faster they're rotating, the more the black hole is spinning. The black hole itself gets spun up as material falls down into it. So let me go to the next slide where you can kind of see it happening. Up on the top, if you have a black hole rotating backwards compared to the material around it, you'll see sort of a spectrum that looks like this. So it'll have this shape. If the two are rotating or no rotation at all, it'll have a different shape. And finally, if it's rotating faster, it'll have this shape. Well, they're actually able to measure these. I don't want to go into too much detail about how it works, but it's literally a general relativity function that happens. Space is being dragged by the black hole, causing that material close to it to rotate faster. So the black hole is actually accelerating that disk of material just outside the black hole. And they saw this. They saw that there's a whole bunch of black holes in the early universe that are rotating way too fast. They rotate super, super fast. And the ones near us, there are some that are rotating really fast, but others that are not. So we think there's two different feeding mechanisms for black holes. There's probably the early universe one, where material was funneled in very quickly and they spun up really, really quickly. And then later, as galaxies sort of merge with the black hole, other material falls in. There's some disturbances on top of it. But that's some pretty neat work. I think, did I think it was great?
We gave it an F.
We gave it an F. We thought it was fantastic.
Yeah, we thought it was pretty good. So, is that frame dragging?
That is frame dragging.
Yeah, awesome. That's why we gave it an F.
That is so cool.
F for frame dragging.
That's that one thing that they're like, I'll tell you what it is, and then they never find out.
It's not dragging the material, it's dragging the space that the material is in, and so therefore...
Which causes the material to...
Yes,
I don't fully grasp this, to be honest. But
oh, right. Yeah.
So now this is one of our favorite upcoming observatories.
Yeah, so the Vera Rubin Observatory will see first light, so that means when it's going to take the first images this summer. And if you think we were excited about the James WST, the James Webb Space Telescope, we were very excited about this, and this is kind of a similar level of excitement for basically everyone in the community, right? James Webb was very exciting for people, again, in cosmology, exoplanets, etc. But this is really for everyone. It's going to be very useful. So it's going to do a 10-year survey of the sky. So many, many parts of the sky are going to be looked at in great resolution, much deeper than before. It's even going to be providing follow-ups for potentially gravitational wave events. So pretty remarkable. Also for dark matter, dark energy, it's going to be able to trace back the structure and formation of the Milky Way better than we ever have. We don't even know some of the things it's going to discover, right? Might discover more asteroids, more comets. And so the AAS had a little conference about it, and it's so exciting. We can't even tell you all the things that will come out of it because we don't know yet. But I can tell you, everyone's really excited. So what did we rate this? And it's going to be in the southern. Did I mention it's going to be in Chile?
Yeah,
so southern hemisphere.
And it's going to be very hard to get time on that instrument, I think.
This the camera is a 3.2 gigapixel camera.
Yep.
So you think your 120 megapixels or whatever on your 200 megapixels is good on your Samsung? No, this is a 3.2 giga. It's insane. We're super excited. It is named after Vera Rubin. She was the astronomer that made measurements of spiral galaxies, measured how fast the outer regions of them were spinning, and they were spinning too fast for the amount of matter that was seen to hold on to it. There shouldn't have been enough gravity to hold that material in place, hence dark matter. So she was one of the people that found evidence for dark matter in spiral galaxies. In fact, the woman. Should have won the Nobel Prize, but didn't get that, but is having this amazing observatory named after her to honor her, which is great.
Maybe even better.
Yeah, we gave it an O. So,
it's pretty amazing.
I totally agree. Rubin is the OG of astronomy. So.
Yeah. Anyway, I still have memories of meeting her at the AAS meeting.
Oh, did you?
Yeah, I got to meet her. So we were all kind of starstruck, I have to say. And astronomers, we don't get that starstruck about people, but the group of us that are around, the UCLA graduate students that I was around, I was a postdoc, we were all like, it's Vera Rubin. And she was super sweet. She was very nice to everybody. So anyway, these are the sorts of things that it's going to take care of and be able to see even more. Forwarding asteroids. And there's the observatory.
Pretty.
Very nice. So,
disks in young binaries. Now, this was done with the ALMA telescope, so it was an interesting story. It's significant because it explores star and planet formation in binary systems. And they found that the disk formation around stars is where the planets get formed. So it's sort of the leftover stuff that didn't flow down into the star. Well, they used these telescopes here, they're radio telescopes, to measure these disks and see how they were making. And they discovered that this star, DF Tau, was actually a binary. There were two stars there. And they formed at the same time. When stars are binaries and they form at the same time. And they thought, well, these disks should be similar. Turns out they weren't. One disk had a lot of material in the outer part of it and almost nothing in the inner part, and the other disk had lots of material in the inner part. So why are they evolving differently? We don't know. Is it planets that are there causing differences? Probably. Is there another little companion mixing things up? Maybe. We don't know, but to be able to measure and see differences in these disks is fascinating. So it was another.
Yeah, we give it a solid G.
Yeah, pretty great story.
Yep,
So,
great
yeah,
story.
it's a pretty good one. So
I love mysteries.
Yeah. Yeah. Now, there's a new NASA mission.
There is a new NASA mission that will be.
Are we going to open up that box?
Oh my goodness. So it is called the Pandora Small Sat mission. And it will be looking very specifically at atmospheres of about 20 exoplanets. These were selected. And yeah, it's going to be characterizing the atmospheres, looking for water vapor. It's actually using a camera that was a double of one made for the James Webb Space Telescope, or one of its instruments is a double or a mission. I don't think we have too much because, again, it's not launched yet. We don't know what it will find, but James Webb Space Telescope had already done some analysis of exoplanetary atmospheres. So exoplanets, again, those are planets in other solar systems, and this will be looking intensely at 20 of them so that we can really get some very good information. So wait and see, but very exciting mission.
Yeah.
What did we rate this?
we give this an M at the bottom,
Yeah.
but I think it should go up.
Really?
Yeah.
Yeah.
I think it should,
Bill, do
'cause
you
it's
agree?
exoplanets, it's atmospheres of exoplanets. It's also a new NASA mission. We need lots of those.
Let's let
so-
Bill decide. Bill,
so-
should we
Well,
move it up or just?
I think the guy who puts the thing up should actually have more
Really?
say than I do. So
All right. I'm going to put it in a K. I'm going to put it in K.
Yeah,
then.
I think that's a good.
Yeah, let's move it up one.
there you go. I mean, he's getting up, sitting down, getting up.
thought we
sitting
were-
down.
This is tough work. Let me
We're
tell
getting
you.
down there. We're getting down to the end. Blue lurkers. Blue lurkers. It's a
want me to
blue
go?
lurker, everybody. Yeah, take it away, Bill.
All right. Blue lurker, I'll try to make this fast. It's really interesting, like astrophysical detective work, I think. A blue lurker is a type of star that blue means it's maybe hotter than it should be, and blue is the color of heat in stars. And lurker means they don't really look immediately different than other stars, but when you start to examine them more closely, spectroscopically and so on, you find all kinds of interesting stuff. It's in M67. You heard of Messier earlier. This is M67, and we have a second shot of M67.
Yeah, it's a star cluster.
Yeah, it's a star cluster. And stars and star clusters tend to form, they form out of the same material, so they tend to be similar in content quite often. They're generally spinning the same direction, and everything forming in these clusters is spinning. That's just what happens.
Yeah.
So there's
Well, they found a couple of stars that are orbiting each other.
exactly.
Yeah.
Wait, are we up to that already?
We are.
Oh, I'm sorry. I thought we had something before that. Okay.
No.
All right. Okay. Yeah, I got it. These two stars were well, it was basically this blue lurker and a white dwarf, which is a burned out remnant.
Yeah.
It's what our sun will eventually be.
Now,
There it is.
the blue lurker isn't the blue-looking one here
Right.
in this picture, because white
That's-
dwarfs are even
the white
bluer than blue lurkers.
The blue lurker is the white one, and the white one, and the white one is the
white
yeah,
dwarf.
anyway,
Yeah,
you
you
get
know
what we're
I'm
saying here.
There
It
was
can be
the
confusing in
The
astronomy.
question was, how
They-
did this happen? Because that star in the upper right, the one you're seeing there, it's a little bigger and a little bluer than it should be.
And it's spinning faster
It's
than it should be
spinning too fast. And then the white dwarf is also too massive. It's
Yeah.
more massive than it ought to be. So it's sort of this odd couple of stars that are out there that needed an explanation. So the team looked at that star, and sure enough, it's bigger than it should be. It's spinning a little too fast. And there was an explanation. And it was there had to be a third star. So how does that
That's
work,
right.
Bill?
So you have this triple star system. Two of the stars are very close, orbiting each other very quickly, like a few days at a time to orbit. And the distant star takes like thousands of days or several years to go around. That's how it starts. Then it gets to the next level where the binary is getting much closer together, and it starts to, before it actually combines, which it will, it sheds all kinds of material. Then it turns into one single star, as we're seeing here, and a lot of the material gets thrown off into space, and the gravitational field of that distant star picks it up, so it gets accreted, which means added to that. That adds mass, which means it's got more fuel, so it's going to burn a little hotter. That's the blue part. The other thing is when material accretes, it tends to spin up the object. So it's spinning faster because of that. Also, finally, the white dwarf, which is the blue star, as we said, the white dwarf was too massive. But that's explained easily because these two stars eventually merged. So it's like two stars merged, went through their whole evolution, and ended up as a white dwarf that's about twice as massive as it should be. It answers all the questions in this weird little, or in the system. Yeah. So now it's just two stars, one of which is really a dead star.
So the whole story here is a couple of stars, a third one, which that third one can take away the angular momentum from the other two. So it allows them to merge on a time scale that we could watch it like this. So pretty neat detective story.
I like what they did,
You give it an M?
We give it an O.
Oh, really?
All the way to the top.
I think we enjoyed the splattering that happened onto
No, I
that
actually
star.
do think it was outstanding work for them to look at all these separate clues and to put together this story.
There was
it's a bedtime story for the ages.
It was 3 sun-like stars, and sun-like stars, like 10% of them tend to be in triple star systems. So this could be happening all over the place. Quite a lot.
Yeah, there was serious shenanigans happening there, and NASA came in and figured it's just set the record straight. And I love it when the receipts show up. So that was great.
Right.
Yeah, bring in the receipts. Now, T Tauri is a young star, a star that has formed fairly recently. So there's lots of dust, lots of gas around. And recently it was learned that it's actually in a double star system. There's more than one star there. And some folks made a prediction that said, hey, this other star that's there has a dusty disk around it, and it's going to start to block T Tauri. And it should start to dim. They made a prediction that T Tauri should dim. So let's fast forward here. Wiki, there you are. So there's Taurus, and you can see the location. Taurus is the bowl in the sky. Aldebaran's a bright red star. So T Tauri is a little bit to the right of the face of the bowl there. And it is, like I said, a double star. They're about 100 astronomical units away. But that lower one, the infrared one, they're in orbit around each other, but it's drifting in such that, again, it was predicted it should block some of the light. Well, sure enough, it's happening. The light is dimming. It's been dimming since the mid-2010s. But we weren't sure whether that was really the Taurus blocking it or whether it was something else happening, just the star changing its brightness. It's a young star. They have variability to them. Well, sure enough, this dimming that's happening now in the last couple of years has been a lot. It's getting quite a bit dimmer. So we really do believe that sort of dusty disk of the close binary is now passing in front of T Tauri. It's beginning to do it. So pretty cool. This predicted dimming seems to be coming true.
Yeah, we give this one an O as well.
Yeah.
So,
I think we've all been waiting for Corona Borealis to explode, and now we've got something else, or not explode. But,
running out of room.
You can move the golden.
I got to move the Griffies here, so hold on a sec.
All right, hold on.
I love a good prediction. Actually turning out to be true.
That's what was great about it, is the fact when you can make a prediction from an observation and then you see it happening, it confirms the physics, it confirms our understanding. It's just it's a good day.
Kind of the opposite of the last story where we figured it out after the fact, as opposed to predicting
although it's still pretty good. Now this one, hot rock entrails.
Yeah, very exciting. There aren't a lot of planetary stories in all the stories we've covered, but this was a very cool one. And this is basically looking at a disintegrating planet, believe it or not. So a planet that orbits its star, and I believe it was about 30 days. And it has a long tail behind it. So very, very amazing that we are able to analyze what
this is an artist.
Yes, we should say this is an artist rendition. We don't have such amazing telescopes yet. One day,
Ruben.
But Ruben, no, I don't think it's going to. No, don't make these kinds of promises. But this is a great way to basically analyze the composition of the planet. So this is most likely a lava world, right? So it's a very, very hot world, and all those rocks, everything is coming off of it. And lots of, I think they found some silicates already. They analyzed in that silicates. But yeah, that long trail behind it. And I think it's a pretty exciting story. There were actually two separate presentations on it. And what did we classify this?
We gave it an A.
I think it's a I think it's
a solid
an
A.
Yeah. And in fact, also to add to this, at the rate at which it is losing mass would be about 1 moon, I think, per million year, believe it or not. Yeah. So it's losing, it's going, it's literally disintegrating.
Yeah. So they see a leading tail, they see a trailing tail. The physics is all matching up with this planet being destroyed by its star, which
sad.
Really? I was going to say it's fun.
It's fun, you know, different views.
It's
of the
fun,
universe.
yeah.
You hate to see a planet go like that.
Right.
Sometimes you just have to go.
Yeah. Well,
If you get that close to your star, you get it.
There's so many planets. We can,
And again, kids, Earth is not going to get that close to
Yeah,
the sun.
yeah,
You got
we're
nothing to
fine.
worry
Yeah, we're
about. This
moving
isn't
away.
This isn't anything to worry about.
we're not disintegrating.
So anyway, 1 moon every million years is
Yeah,
the amount of mass.
years.
There it is, and then it'll take 1 to 2 million years to destroy. So eat your Wheaties, kids. You can watch
we'll
it.
report on it again when that.
That's right. Come back in
We'll get back to
in
you
a
on
few
that.
million years.
Now
That's
I
right.
think we are to our final story.
That's right.
And we're just doing okay on time. It's not 9 o'clock yet. Resolving 90 million stars. 90 million. And resolving means seeing them as individual stars. So you can look at a galaxy, and there's hundreds of billions of stars in a galaxy. But how do you resolve 90 million stars? Well, here's your hint. That's Andromeda that's up there. Andromeda is the nearest large spiral to the Milky Way. It's a little bigger than we are, a little more massive. It turns out we actually think that it probably suffered a big interaction recently. We see signs of that, work that I've been on and have been affiliated with. We're seeing merging going on in Andromeda. It'll eventually merge with us. In about 3 to 4 billion years, our galaxy will merge together with it. But the Milky Way is hard to study. We're within it. It's like trying to study a forest if you're in it. All the trees block your view of the other trees, so you can only see so far. Andromeda, we have an external perspective. We can study it from above. It's about 3 million light years away, so we're seeing it 3 million years ago. Well, there was a study by Julianne Del Canton, professor up at UW, wonderful astronomer, and she thought, well, let's use Hubble, and we'll just take a bunch of tile. We'll tile it. We'll do many, many, many frames and stitch them together and make a giant image of Andromeda. And that came out, 5, 6 years ago, maybe longer. And now her colleagues, I want to say it's Brian Williams, but it might not be. I could be crazy. Anyway, he's leading this, but a colleague of hers, she's on this project too, as is my PhD advisor, Raja. Hi, Raja, if you're watching. They decided to do the FAST survey. The first one was called the FAT survey, P-H-A-T, which is the Panchromatic Hubble Archive Treasury program, I think. And then the FAST, it's the southern part of it. S stands for south, so they're looking at the south part. Indeed, they stitched together not the whole galaxy, but a huge, huge freaking chunk of it. And you can see individual stars. You can measure their brightness and their color, so you can figure out their spectral class. Color and spectral class match, by the way. You can see the red ones versus the blue ones. So you can select out stars and say, just show me the very young ones. That's the ones in that purple box up to the left. Or show me the just young ones, or the intermediate aged ones, or the old ones. You can go in and make images from those by selecting out the individual stars. Now, I love this work. This is the sort of stuff I did. This is called stellar populations. It's kind of old astronomy, the old way of doing things. But you can see the young stars are super clumpy. They track the spiral arms. The young ones also track the spiral arms. The intermediate aged ones, they've drifted away from those spiral arms. They've had time to orbit multiple times, disturbing that spiral pattern. And then the ancient stars, the really old ones, you barely see the spiral pattern at all. Now the dust there, those clumps you're seeing, that's dust blocking it. That isn't any clumping. So very, very fun result. I love this team. They're amazing people. But the FAT survey had already been done. So they had already done the North. This is an extension of it. So I don't think we quite rated it an O.
Yeah, we gave it an F.
Yeah, I think
so.
it's fantastic work.
Yeah,
It's
it's
carrying
fantastic.
on
It is fantastic.
the amazing work that's been done, because they've been able to select out colors and the shapes, and they learned about the clumpiness from the FAT survey. But to complete it and to finish it there is amazing. Now, there's a new space telescope coming that's going to be able to do this in about 6 pointings. So we'll redo all of it with the new space telescope when it comes.
So they can
That's
get the spectrum of each of those 90 million stars?
No, we have to go back and do follow-up spectroscopy
okay.
if we want actual spectra. In fact, most of these stars are too faint for our current generation telescopes. You can get the red giants like I did. I got spectra of red giants. I was the first person to get individual stars in Andromeda. But
Big deal.
yeah, it's fun. It was neat. They've pushed it a lot further. They've gotten a lot more data since then. But with the 30-meter telescopes, we will start to be able to probe further down and to be able to measure these. So the exceptionally large, the ELT that the Europeans are building, it'll come online first, and it'll be able to see Andromeda. So it'll be neat. Yeah, we got a question over here.
What does stellar mean?
Stellar means star. Yeah, so it means it's a star. So if something is stellar, it's star-like.
Or it's a great compliment.
Yes.
Something
If
stellar,
you're stellar,
it's amazing.
something
It's
like
brilliant.
It
Stellar,
means you're
that'd be
brilliant.
really-
It's a great comment.
Really great, really wonderful.
So we are to the point of the show where we want you to pick which of these stories you think deserves the top award, the
sun.
Golden Griffey, the Silver Award, the Silver Griffey, and the Bronze Griffey. So, to make this simple so we don't have to read out, say, 50 ones, should we just go off the O tier? Are you comfortable with that, everybody? Yeah? Okay, so, Jared, why don't you point at them?
Okay, sure. I'll go ahead. I'll give you.
Okay, and let's turn on our applause meter booth.
All
right.
This will get the applause meter ready.
Get ready.
We're
All
gonna
right,
go
so
in
the
reverse.
dimming of Titori. Who wants that one? Raise your hands and applaud if you love it. Yay.
Sounds like every time I make a
Wow.
joke.
So that's
All right,
okay.
so-
All right,
That's the
so
fourth.
blue lurkers.
Blue lurkers.
Who likes lurkers? Okay.
That's right. Okay. I'll have the Vera Rubin Observatory.
Yay.
And then moments before solar.
Yes! Yes! Woo!
I think you're putting your hand on the scale there.
Yeah,
Laurie.
a little bit.
All right, so I think it's between the first two. Do we want to have a
vote off?
competition? A competition? So anyway, a vote off. So raise your hand if you want Vera Rubin to win.
What are you guys talking about?
Raise your hand if you want the solar flares to win.
Again, the sun's right next to us,
I think
everyone.
Vera Rubin edged it by just a nose, just a nose. So the winner of the Golden Griffey is indeed the Vera Rubin Observatory that's coming
Well
online
played.
You
next
gotta be
year.
happy about that, right?
The
Yeah.
Silver Griffey goes to the moments before the solar flares, and the Blue Lurker gets the Bronze Griffey. So we'll be sure to email the researchers this wonderful award. They're going to be thrilled.
I'm sure.
They really will be.
Let them know this prestigious moment in their career.
Exactly. We only do a show this chaotic, well, every once in a while, but certainly once a year it gets this chaotic with this sort of thing. So we hope you enjoyed this tonight. We do have, by the way, I want to remind you that we have a real prize winner, Dr. Andrea Ghez, who won the Nobel Prize for her work discovering or proving that we have a 4 million solar mass black hole in the center of the Milky Way. Her work led to that. She shared the Nobel Prize with Gensel that year, but she will be here next month. So it's going to be wonderful. Come on back for that. So I'd like to thank the panel tonight. Thanks to all three of you. I want to thank our team that helped produce all this wonderful artwork and all this research. It was a lot of work this month, of course. So thank you, everybody. I want to thank our tech crew. They don't get enough mentions back up there. And our social media crew, too. The folks that help promote the show. Pixie, I'm looking at you up there. Thanks to you, too. And our art team, Ella, and everybody. And Griffith Observatory, thanks all of you, the people that tune into our events and come to visit Griffith Observatory. Tonight's program is brought to you by Griffith Observatory, the City of LA, the Department of Recreation and Parks, and we do always thank the Griffith Observatory Foundation that makes so much of what we do possible with their generosity. So thank you, Griffith Observatory Foundation. And we'll see you next month, everybody. Thank you so much.